Saxon Algebra 2, Lesson 115. Our topic today is going to expand on our study of exponents. We're going to use some of the tricks and tools we've learned with Lesson 113, which was about logarithms. We're going to play with that. The first piece of this is to talk about exponential equations. What is very cool about exponents is, let's say we have a little equation that looks something like this. We have an equation. We have one term on each side of the equation, and it's a base with an exponent. The bases match. When we have a scenario like this, we can take the exponents off of the bases and solve them as an equation of their own. Only because the bases match, and only because we have one term on each side. There's no other pieces to this equation. So we can take these off and simply solve these. I put decimals on this side so I would be able to subtract it. This goes to x equals, and then if I go 2 minus 1.23, I'll get the positive version of this answer. I'm just subtracting. 7, 7, nothing left, okay? And that's negative because the 2 is the negative. So I can solve this confusing looking equation by getting the bases to match and then pulling the exponents off and solving them separately. Now let's look at, that wasn't technically an example. Let's make it one step harder. What if we get an equation that looks like this? We've got base 10 with an exponent on one side, but this side is not written as a base 10. How are we going to solve that? The trick is to use what we know about logarithms, specifically the buttons on the calculator. We want to change 17 to 10 with an exponent. Every number can be expressed as a power of a base. We can do it with any base we want. The calculator is set up for 10. We know we want 10 because we want the bases to match, and that one's a 10. So we're going to need, we know the number we want and we know the base we want. We just have to find the exponent. So that means have the number, want the exponent. This is the button we'll use. So we enter 17 into the calculator and then use this button, and the answer that we will get is 1.23. Oh, look, it's just like before. We were setting ourselves up. So what we know is that 17 equals 10 to the 1.23. And now we can rewrite, substituting this in for 17, 10 to the 1.23 equals 10 to the x plus 2. That's right where we started off with this. We know that we can take the exponents off. So we get 1.23 equals x plus 2. We subtract 2 from both sides. We already did that up here. We know that x equals negative 0.77. Okay? This answer is neither an exponent, a base, or a number in our sense of that, but it is an algebraic solution to this original problem. Okay, so it's a variable that was in the exponents. So don't hurt your head trying to figure out how this relates to logarithms. This doesn't, this is just an algebraic solution. Okay, so we're going to start playing around with this. When we see a base, a power of 10 on one side, or it could be a power of e. It'll be one or the other because that's how our calculators are set up. But when we have this on one side, we can convert the other side to match by using these functions on the calculator. This for base 10, this for base e. All right, now, why would we want to do that? Oh, let me tell you. Now we're going to talk about exponential functions. This whole chapter is about exponents. These are the functions. Now, we are living in an exponential function right now. COVID-19 is a disease that behaves as a exponential virus because, just to give you a quick sketch of how they look, this is time, and this is number of infections. As you have probably heard, and I'm not drawing this mathematically precisely, but as you've heard, it starts out slow and it doubles. So the rate of growth, the number of infections, increases by, I believe with COVID it's doubling. But it's not just adding 2 every day, it's faster than that, right? This is what an exponential curve looks like. Sometimes we'll have what's called an exponential decay. This is growth. And sometimes we'll have what's called an exponential decay. And that is when it starts out high and it drops at a faster rate. Okay? So we're going to deal with word problems that use either of these scenarios. What is cool about these is that there's a simple formula that we're going to use. It's on page 466. I'm going to copy it right here though and explain it to you. All right. A equals the amount of something, the amount of COVID-19 present in the population, as an example. We don't have any COVID-19 problems. John's not quite that cutting edge. T equals time. It can be years, hours, weeks, months. It doesn't matter. It needs to be consistent throughout the problem, but John is kind to us on that. So AO equals the original amount. This will all make sense once we see the problem. And then A to the T equals the amount after a certain time. This will all make sense, I promise. Okay, so that describes this variable and that one. K is a constant. That we will be given, I think. We're gonna solve for K. We're not going to be given it. That's for Algebra 1ers. We're going to calculate it. And then E is the natural log. Okay? So this is a great example of how the natural log works in science. Okay? So this is the formula. This is what all the variables mean. Keep this handy as you're doing these problems so that you can keep track of what the heck we're talking about. I'll probably be flipping back and forth to it as we go. All right. Example 115.2. We're on point 2 because number 1 was that calculation problem, which guess what we're going to use. In the beginning, there were 400 bacteria in the dish. Okay. That sounds like the original amount to me, 400 bacteria. I'm going to rewrite our formula up here. These are exponents. This is like a subscript. That's a 0. Or it's a letter O. You can think of it either way. I'll say more about that as we go. This is the original amount, okay? Some people think of this as an O for original. Some people think of this as a 0 for time 0, right? It's at the beginning, so the time is at 0. Either way makes sense, either way works, whatever your brain wants to do. The number of bacteria increased exponentially. Okay, so we know that this equation will work. 3 days later, okay, so when t equals 3, there were 2,000 bacteria in the dish. Let me change that into a t. I don't want to confuse you. AT equals 2,000. I was taking a little shortcut there. How many bacteria would there be in 8 days? Okay, so the first thing we need to do, these are two-steppers. The first step is to solve for k. Okay. So we take our formula and we take the data for the first scenario and we use that to solve. Okay, so I'm going to take my formula, a to the t after 3 days, right, because we said t was equal to 3 days. That was 2,000, so we can say 2,000 equals a to the 0 or a to the o, the original amount, is 400, times e, our calculator knows what that is, we don't have to tell it, times some constant, times t, which is 3. Okay, so we plug these 3 values into the original equation, and that's going to allow us to solve for k. Remember, e isn't really a variable. It's just a shorthand way of writing 2.72 blah, 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 blah. Or it's 2.718, I believe. Blah, 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 blah. Okay, so that looks good so far. We have to solve this for k, though. And that looks a little dicey and hard, doesn't it? But let's start by just dealing with these big numbers. If we divide both sides by 400, that'll get rid of the numeric coefficient and leave us just the e. This then becomes what? It's just plain 5, isn't it? 5 equals, and then that cancels, e, and I'm going to write it in the order that feels more normal to me. I'm going to put the number first. 5 equals e to the 3k. Oh, okay. This is what we saw before. If we could make 5 into e to the power of something, if we could rewrite 5 as e to the power of something, then we would have e equals e, and we could take the exponents off and solve for k. Yay, let's do it. So we go to our calculators, and we enter 5, and then which button do we want to pick? Let's see, we know the number and we know the base. We want the exponent. Ha, have the number, want the exponent. So we do this one, it's the natural log button, the ln. We bump that bad boy out that 5 equals e. One second, let me just finish doing this. It's the ln, and we get 1.61. Okay, so this is our little side calculation. So now we can write e to the 1.61 equals e to the 3k. If you're ever wanting to check this, you can by taking 1.61, that's the exponent, enter 1.61 into your calculator, then tap this one. We have the exponent, we want the number, and what you should get is 5 back again. That's how you can check your work if you're ever not sure that you did it the right way. All right, now we've got matching, oh wait, I wrote this one. You've been probably sitting there looking at that 3 going, what? I just copied it wrong. I was so busy thinking about this 3, I made that into a 3. but this is the same. This hasn't changed on this side. We just rewrote the 5 as e to the 1.61. Now, because we only have one term on each side and they both are base e's, we can take off the exponents and solve them as their own little equation. So we will divide both sides by 3. And that tells us that k equals 0.537. Okay? That's step 1, you guys. That is step flipping 1. All right? Now, what we need to do is use our equation again, but this time we're going to go back and we're going to solve for at when t equals 8. All right? So, I wish I could show 2 pages at once. This is when I wish I was on a whiteboard. Okay, so here's what I'm going to do. I'm going to rewrite the equation. All right, we want to find a to the t when t equals 8, right? And we just calculated that k equals 0.537. Okay, this is, now we're at step 2. We don't need the other data because we use that data to solve for our constant. So now we can say a to the 8th, because that's what we're looking for. I'm taking this equation and writing in, equals our original amount. I'm looking in the book. The original amount was 400. We had that written on the previous page. Times e to the k, 0.537, times 8, which is t. Aha! Okay. So, now what we want to do is solve this. Luckily, all our variables are right, correct? The right side, this isn't a variable. We just need to run this through the calculator and we'll have the solution. So here's the way we do it. We work backwards. First, we multiply these two together. 8 times 0.537 is e to the, I don't need the parentheses anymore, 4.296. Okay? That's just multiple, that's the thing I did first. I multiplied those together. Now, I'm going to calculate e to the 4.29. I'll be using this button, right? Because I've got the exponent, I want the number. So I'll enter my exponent of 4.29, then I tap this button, and that will tell me the value of this expression, which is 73.4. Follow along on your calculators and make sure it's working. Okay, the 400 I haven't changed at all. I'm changing these as I go. And then my final step is to multiply those two together. And I'll get that the amount of bacteria that we have after 8 days is equal to 29,362 bacteria. Okay, you guys, this is such a perfect illustration for our time. I don't know the constant for COVID-19. Nobody does, I don't think, at this point. Maybe they've built some mathematical models. But what started out as 400 bacteria has now, in 8 days, in just over a week, it's at almost 30,000. That's a perfect illustration of what's going on in our world, and it's a beautiful story about exponential growth. Okay, I told you that there was also this thing called exponential decay, which works the same way, and the good news is you don't need a separate equation. The same one works. I'm going to rewrite it. Okay. The amount at a certain time is equal to the original amount times e raised to the power of a constant, and then the time. In the beginning, there were 4.25 ounces of radioactive material. So the original amount equals 4.25. We don't need to put the unit on there, it's fine. It decayed exponentially. Yay, we get to use this. 10 years later, when t equals 10, 3.92 ounces remained. This is how radioactive material works. It decays, right, and it drops over time. So that makes sense. We're seeing a decrease rather than with the bacteria we saw it increase. 10 years later, oh no, that's what I just said. How much would remain after 30 years? So we're supposed to find the A of 30, all right? That's the time. Okay, 2 steps, just like before. The fact that this is decay doesn't change the way that we attack the problem. It just changes the kind of answer we'll have. Okay, so the first step is to find K. So we start with the first bits of information and we use this to solve. So 3.92 is the amount after 10 years equals the original amount, 4.25, times E times K times the time, which is 10. And we end up with this formula. We always end up writing the number after the letter, which always bugs me, but we'll fix that as we go. All right, looks good. So what did we do last time? Oh yeah, we need to get rid of this big fat numeric coefficient. So we divide both sides by 4.25. You can do that on your calculator. I'm going to use John's number, and we get 0.9223 equals E, and why am I doing that? E to the, I'm flipping it, 10K. I'm just flipping those around, okay? So all I've done is just divided these numbers. This one disappeared, and this reduces to 0.9223. And here I just flipped the letters. Okay, now I'm at the point where I'd like to rewrite this number as an exponent on the base of E. So I've got the number, I want the exponent. That means I need this button, the natural log. I have the number, I want the exponent. Okay, so I plug that in, and I find out that this number can be written as e to the 0.08. That's what happens when we have decay. We're going to have a negative exponent. Well, that's not necessarily true. I take that back. But that negative exponent, and it equals what we have on the other side, e to the 10k. Now we have single terms on each side, matching bases, so we can say that negative 0.08 equals 10k, and I can divide both sides by 10, and that tells us that k equals, one more decimal place, right, 0.008 negative. That's not the way I wanted to write that, but okay, that works. It's a negative number, okay? So there is our k. Let me just work up here. I don't want to copy to another page. So there's our constant. Now we need to find a to the 30. So a to the 30 will equal the original amount, 4.25, times e times 30 times, I'm going to write it down a little bit because I need the space, minus 0.008. Okay, so that's up here. It's part of the exponent. Now that's going to bother me. Let me write it on the other page. A to the 30th equals 4.25 times e to the 30 times minus 0.008. There. That looks better. All right, now we're ready to simplify this, and it looks kind of overwhelming here, but we're just going to work from the back end in this way. So the first step is we multiply those two together. And what do we get? It is 0.7866. If you multiply those two together, oh no, John doesn't show me every step. This is the whole calculation. He multiplies those two together and then he uses this button to write that as a number. So first you multiply these two together and then you use this button to take that number as the exponent, enter it, tap that button, and it will give you the value of this, the number, and that is, I'm just crossing out this whole line, 4.25 times 0.7866. Double checking to make sure I copied that right. Yes, I did. Okay, so John doesn't show it. Last time we showed it in two steps. First we multiplied those, then we found the value of e to that power. John just does it in one jump this time, and that is the value that you get. And then the final step is just to multiply those two together, and we get that A, the amount of radioactive material you have after 30 days, is it? Years, is 3.34. And it's nice to put the unit back on when we're done. Ounces of radioactive material. That is our answer. Yay. Wow, this lesson is a workout because we're still not done. Exponential functions, exponential growth, happens in business too, because when we earn interest on money that we have placed in either a savings account or a money market account or something like that, something that earns interest, it follows an exponential curve. The reason it does that is because if you put $100 in the bank and you're earning 10% interest, then at the end of the first year, you'll have $110, right? You earn 10% a year. That would be a really good rate. I would be pumped to have a bank that paid me 10% per year on my savings. But at the end of the year, you're going to have the original $100, plus you're going to get 10% of that in interest, right? Now, the next year, you're going to have your original $100, plus you're going to have 10% of this amount, assuming you didn't take any out. So now you have $121, okay? The next year, if you leave it in, you'll get $12 of interest, and so that will be $133. So you see that as your balance goes up and you continue to earn 10% on the total balance, you're going to get that nice exponential growth. That's why it's a great idea to save when you're young, because then that money will sit there throughout your lifetime and just continue to earn this really fabulous exponential rate of growth. And then you'll have lots of money when you're older, but it never works out that way. But anyway, it's a great plan. So we can use the same model to calculate compound interest, and that's our final problem in a very long lesson. The same formula works. We just fine-tune it a little bit for some business words. Okay, a to the t, that's the same as we had before. It's the amount after a certain amount of time, equals what we call the principal, which is the same as the original amount. amount. Principal is just a business word that means the original amount of money you invested. In our little example a minute ago, it was $100. E is still the natural log. T is still time, but the R, instead of having a constant that we have to figure out, that's just the interest rate. Okay, so in some ways these problems are a little bit simpler when we have money because we don't have to calculate the interest rate. All right, and so what we're supposed to do is we're supposed to find the amount after 10 years. Oh, sorry, I haven't written all this down yet, have I? Roger deposited $5,000 in an interest-bearing account. Okay, so his original amount, which is equal to principal, same difference, equals $5,000. I'm just helping you see that this is similar to what we did last time with a few little superficial variations. Excuse me. Oh no, my hiccups made me yawn. And his interest rate is 7.5%. So R, the interest rate, equals 7.5%. How do we write that as a decimal? Okay, 7% would be like this. 7.5. We add that one. That's confusing and kind of a little mind bender. So just remember, 7.5% looks like that. Oh wait, you won't be fooled again. How much did he have in 10 years? So we're supposed to find the A of 10, the amount in 10 years. All right, like we said, we don't have a constant. We just set this up once and grind the numbers through. So the amount that he'll have in 10 years is equal to the original amount, 5,000, times E to the 0.075 times 10. All right? The principal, the interest rate, and the time. Well, that's not so bad, is it? This looks a lot more manageable. We don't have to divide anything away or go through those steps. We're just simplifying right here. So we work backwards. The first step is to simplify those. We have 5,000 E, and that's going to bump that so it's to the 0.75. We have the exponent and the base. We want the number. So that's this set. We use this one. We enter 0.75 to the calculator and then tap that button. That will give us a value of 2.12. And then if we multiply those two numbers, we simplify that, then we multiply these two numbers, and it is 10,600? Yes. $10,600. That is the amount that we will have in the bank after 10 years. So you put $5,000 in the bank, you leave it alone for 10 years, and it has doubled and then some. Not too shabby. So this is how we can tweak our exponential function problems ever so slightly to be used in a business context to calculate how much money you're going to have after you get your interest compounded. Slight variation of the formula, but really the same idea. Oh my gosh, finally we have reached the end of lesson 115. That was exhausting, but you're now incredibly smart, and I hope you just take a deep breath and go do something good for yourself right now. Thanks, bye.